as we have discussed the concepts of the designing of the FIR filter using the windowing method, today we are just going to describe in details. As we have discussed the basic concepts, now we are just going to elaborate all the concepts which will be utilized in order to design the FIR filter using the windowing method here. And for that purpose, we will also consider here some examples so that we can make clear ourselves that how the FIR filter will be designed by the given requirement or the specifications. Here we will consider here the linear filter design concept, and as we know, it is used to be like an art, and now there are so many tools and software available in order to design the optimal filter. Here we are saying the optimal filter because it is a compromise between the cost and performance of the filter. For DSP, there are the two common classes of the filters, two design methods. One is for the recursive method, and the second one is the auto here the moving average method. That is, the first one is the IIR and the second one is the FIR. Both classes use finite order of the parameters for the purpose of the designing, because as we know, in order to analyze the performance of any system or the filter, we have to compare the four parameters, and these four parameters are: one is the speed, that is related to the delay, propagation delay of the algorithm or the here the system itself, and the second one is the power consumption, that is the power used in order to either they execute the algorithm or utilized by the system here, and the third one is the space, space either in the on the silicon wafer or in the form of the memory space. And the fourth parameter is also very important when we use here the digital signal processing, because during the time of the digitization, there is a need of the processing. So the fourth parameter is the finite word length effect. So during the time of the designing, we have to focus on the optimal concept, and after the designing, we have to cover these four parameters in order to analyze the behavior of the design system. And for that purpose, there is a need of the finite number of the components, and for that purpose we have to use the finite order of the parameters for the purpose of the designing. And here we are just going to cover the FIR designs which we have mentioned briefly in the previous lecture, and after that we will come to the here the IIR designing concept, and after this designing we will come to the next topic, that is the design of the IIR filter here. Now we are just starting here the concept of the designing. Suppose any filter has to be designed and requirements are given, that is the given desired frequency response is given in the graphical manner, and that can be represented mathematically in this manner by taking SDE to power j omega, and by taking the inverse Fourier transform of that graphical representation or the mathematical representation in frequency domain, we will get here 1/2 pi integration from minus pi to pi SDE to power j omega e j omega d omega. And this is the inverse Fourier transform of the ideal filter here. And in this case, there are the infinite number of the sequences, or we can say there are the infinite number of the coefficients. And if there are the infinite number of the coefficients, then naturally the components which are required must be infinite, and that is not physically realizable. So we will convert these number of the components in the finite number of the components here. Then after getting this inverse Fourier transformation, we have to obtain the mth order, that is a finite order related to the causal FIR filters. See here, we have to focus on these 2 points. One is the mth order, that is the finite value, and the filter nature must be the causal. In this case, the nature is anti-causal, allowing for the negative as well as the positive values here, but the filters must be the causal here. So how it will be done? By truncating the HN. So how the HN will be truncated here? By shifting with the help of the say some window here, SDN will be multiplied by the omega n here, and now n will be a finite number having a value between the 0 to capital M, where capital M is less than infinity. Otherwise this HN will be considered as the 0. These concepts we have discussed in the previous lecture, and now the same multiplication in frequency domain can be represented with the help of the periodic convolution concept, that is the convolution of the HD e j omega, that is the desired frequency response with the frequency response of the selected window here, W e to power j omega here. Now, if we consider here very simple window, that is the rectangular or the boxcar window here, then that window in frequency domain will be represented W e to power j omega e to power minus j omega m by 2 sine omega m plus 1 divided by 2 upon sine omega by 2. And we have derived this relation in the previous lecture here. So here this is the HD e j omega, that is the impulse response has been converted into the frequency domain, and in frequency domain representation is the HD e j omega, and it has to be periodically convolved with the selected window, and the window is in the form of the sinc function. So after the convolution we will get this type of the window here, and this is the upper side is the amplitude response and the lower one is the frequency response of the selected window. And we have also observed these type of the graphs during the time of our lab work, when we had used the concept of the MATLAB or the functions related to the MATLAB. Now this is the frequency response of the filter which has to be designed. But this is which type of the frequency response? This one is the amplitude response of the here the optimal filter that has been specified from the required filter that has to be designed. I am repeating it, that is requirement to specification. Requirement is ideal, from the ideal we have specified this one that has to be designed here. Now if we again see this filter after getting the convolution, then we will find what is the modification. This one was the ideal, dotted black lines. This was the ideal frequency response existing from minus omega c to plus omega c. After some practical approaches, we have converted into the form of the specifications, and now what is the additional points which have been included in this physically realizable filter are the pass band ripples, means some ripples will be allowed in the pass band, or permissible range of the ripples in the pass band. And what is the another parameter? Stop band ripples are also have to be considered, means we have to consider the permissible range of the ripple in the stop band, and at the same time in place of selecting the transition width 0, now there must be some significant value of the transition width here. So we have included here the 3 parameters, and we have also gone through these 3 parameters in the previous lectures, and we have concluded that these 3 parameters, that is the pass band ripple, stop band ripples, are the ripples in the pass band, ripples in the stop band, as well as the transition width. These 3 parameters must be considered like the 3 angle of a triangle. When we are trying to improve any one parameter, then this improvement will be achieved at the cost of remaining 2 parameters, and vice versa is also true here. So so on the basis of the need and the requirement, we have to select the different types of the approximation. Okay, so now we will consider here the different types of the windows for the different purposes. For example, in the first one we have discussed the rectangular or the boxcar window, and other taper windows are the Henning window, and here the Hamming window here. And these are defined by MATLAB command. We can get these window by these commands here, the m plus 1, Henning m plus 1, or the Hamming m plus 1, where the m is the length of the window. And we have discussed these commands as well as these mathematical equations in the previous lectures here. Now we are coming, and we have also discussed one more window that is related to the Kaiser window. And the Kaiser window is a trade-off between the ripples as well as the transition width, that is the side lobe attenuation and the transition width. And for that purpose, we have used a special type of the function, that is the I naught beta here, and we have defined the different values of the beta for the different shapes. So here now, if we consider a trade-off between the ripples versus transition width, say see here that if we consider the two windows, one is the boxcar, that is the rectangular, and the second one is the triangular here. Now, if we compare these two, then we'll find that triangular has the wider bandwidth, wider main lobe bandwidth here in comparison with the boxcar. But what is the drawback? What is the advantage of this one? The advantage is side lobe attenuation is larger than that of this boxcar here. And the same can be, and here we have used the range from 0 to 1 positive side and 0 to minus 0.2 in the negative side. And if we consider here the 0 to minus 70, then we can compare these results something like in this manner here, that is the boxcar and the triangular is given here. And the one is the here the normal graph, and the second one is the logarithmic one. Similarly, we have, in the second example, we have considered the Hanning and the Hamming window. Here, similarly we can compare. If we see the magnitude response, then we will see that more or less performance of the Hanning and Hamming window are approximately considered to be the same. But if we consider here the main lobe width, then the main lobe width of the Hanning window is slightly less than that of the Hamming window here. And side lobe attenuation of the Hamming window is slightly greater than that of the Hanning window. So these are the comparison, and according to these concepts, we can compare the performance of other windows here. And we have also discussed these concepts in the previous lectures. Hopefully you have performed the related experiments in the laboratory, and you have compared the performance of the different type of the windows. Or nahi kiye hain, then please do it. Now, for the purpose of the designing, what we have to do? See, we are just going to describe the steps, and then we will consider one example. So far, we have discussed the basic concepts, how the filter will be designed using the window method. And we are just going to describe the steps in order to design the filter here. So what has to be done? At the first level, choose a desired frequency response that will be named as the HD e to power j omega, and it must be the non-causal, that is the zero delay and infinite impulse response. And if derived from the continuous time, then choose T, that is the sampling time period, and use the formula HD e to power j omega HC j omega by T. And then we have to use the length of the window. Window length must be equal to the m plus 1. And what is the purpose of this one? This affects the transition width. And type of the window, it affects the transition width and the ripples both here. And the modulate, window modulate to shift impulse response here. And see here, whatever is the response in frequency domain, that will be modulated by e to power minus j omega m by 2. Now determine the truncated impulse response, H1n. Truncated impulse response. See here, this is the truncated impulse response, not the windowed impulse response. Truncated impulse response, Hn. 1 upon 2 pi minus pi to pi HD e to power j omega and e to power minus j omega m by 2 e to power minus j omega n, in order to shift the negative portion towards the right side. That is in order to avoid the negative portion, that is the anti-causal portion, that is the truncation will take place here, and the n will lie from 0 to capital N. Now we have to select the window, and then we have to apply the window here in order to get the windowed impulse response. Again repeating, this is the truncated impulse response, and the next one will be the windowed impulse response. Here this truncated impulse response will be multiplied by the selected window, and then we have to check here and we have to compute here the frequency domain representation of this one windowed impulse response, if whether all the specifications are meeting to the required value or not. If not, if we are not getting the satisfactory result, naturally we have to change the value of the M, or we can change the type of the window here, or both. Now, if we consider here the very simple example, that is the HD e to power j omega is 1 in the cutoff frequency range of the omega starting from the 0 to omega c, either side, plus side or the negative side. Otherwise, it will become the 0. That is the low pass filter here. Now we'll select the M, that is the window length, and set H1 e to power j omega, that is the related to the truncated value, HD e to power j omega e to power minus j omega m by 2, and hence we will get here the truncated frequency response, that is the H1n, and this will be the inverse Fourier transformation of this one, that is the sine omega c n minus m by 2 divided by pi n minus m by 2 in this range when n is lying between the 0 and capital M. And it has also been derived in the previous classes here. Otherwise, this value will become 0 here. Now, if we apply here some manipulation, then we will find that it is nothing but this one is a sinc function, that is represented as omega c by pi, sinc omega c by pi multiplied by n minus m by 2. So this is a sinc function here. Now, windowed sinc function means this truncated impulse response will be multiplied by the window function Wn here, and we will get the Hwn. So from the Hn, we have to derive the H1n, that is the truncated impulse response, and then we will get here the windowed impulse response, Wn multiplied by the H1n, that is the sinc function omega c upon pi, sinc omega c upon pi n minus m by 2. This is the impulse response of our desired low pass filter. And if we have designed any low pass filter, then accordingly we can design here the high pass filter or the band pass filter by applying here the transformation method. So first we will design the low pass filter using the window method. So what we have learned during this discussion, that if any ideal filter has to be designed, then that requirement means that ideal filters requirement has to be converted into the physically realizable form. And how it will be done? When we consider the inverse Fourier transform of the ideal filter, then we will get that it exists for the infinite duration, and it exists for the positive as well as the negative values of the n, that is, it is anti-causal also. And what is our approach? Our approach is to select here the finite number of the components, means we are interested in order to select the finite number of the coefficients. And for that purpose, we have, and at the same time, we are also interested to consider only the causal response, because anti-causal means physically not realizable concept. So not realizable concepts has to be converted into the realizable concept using the here the truncation, and after that, in order to achieve a trade-off between the here the main lobe width and the side lobe attenuation, we will select the different types of the window, and the truncated impulse response will be multiplied by that selected window. We are again repeating it, that we have to multiply the truncated impulse response with the selected window, not any random window here. The selected window means there must be a criteria in order to select the window, means which window will be selected for the purpose of the designing of the filter for the required mode here. Now, if we consider an example, say the example 1, design a low pass filter with pass band edge frequency is 0.4 pi and stop band edge frequency is 0.6 pi, and these frequencies are in the digital domain. And as we know, in the digital domain, range is from -pi to pi, and generally we consider from 0 to pi here. And the omega p, omega s is given, which exhibits a minimum attenuation. We have to see all the components related to the specifications. Exhibits a minimum attenuation greater than 50 dB in the stop band. If we see and if we recall the representation of the just coming to the previous slide, let's see here this one. If we consider the truncated value of this one, then we have to consider only the right side of this one, that is 0 to omega c here, and then we will find there is attenuation in the pass band, and this is the maximum attenuation that is possible in the pass band here. And because before this one, whatever is the attenuation, that is lower than that value here. So this value will be named as the maximum attenuation in the stop band. Now we come in the pass band here. In the pass band, whatever is the attenuation, that will be known as the maximum attenuation in the pass band. Now we come to the stop band here, then we will find that this value equal to the first side lobe, or this one, when it crosses the stop band edge, it is the minimum attenuation. It is the minimum attenuation that takes place, because as we are moving towards the right side, here the value of the attenuation increases. We will count the attenuation from this value towards this value here. So in the stop band attenuation, at the stop band edge frequency, whatever is the attenuation, that will be named as the minimum attenuation in the stop band. And in the pass band, whatever is the attenuation at the pass band edge frequency, say something somewhere at this point, this will be named as the maximum attenuation in the pass band. So again, coming to the example, it exhibits a minimum attenuation greater than 50 dB, means 50 dB must be the attenuation at the stop band edge frequency, at least at the stop band edge frequency in the stop band here. So for this purpose, first of all, we have to select a particular type of the window, and then we have to select a length of the window, because if we move to the previous slides again here, then we'll find that it has to be truncated on the basis of the M. That is, we have to decide the length of the M. And after truncation, it will be windowed with the help of the window function WN, means the type of the window or the selection of the window is required here. So at the first level, we are trying to select the window, type of the window, and the length of that selected window here. Now choose the window type here. An ideal low pass filter has infinite attenuation in the stop band. If we again come to the point here and see what is the attenuation in the stop band for the ideal filter, here this attenuation is infinite in the stop band. But it is not possible for the practical purposes here, and the value of the attenuation is given that it should be minimum 50 dB in the stop band. An ideal low pass filter has infinite attenuation in the stop band when we approximate an ideal filter with a practical filter. Using the window method, we accept some approximation, and that's why there will be the approximation error. Now the peak approximation error depends on the type of the window and is known for each window as reported in this table here. Now if we select the rectangular window, then the peak side lobe amplitude relative value of peak side lobe amplitude in dB will be -13, and approximate width of the main lobe for this type of the window, it will be 4 pi by m plus 1, and the peak attenuation error, approximation error, that is that 20 log delta in dB, this will be equal to the -21. And for the Bartlett window, the peak side lobe attenuation in dB, this will be equal to the -25, and the approximate width of the main lobe, this will be the 8 pi by m, and approximate here the error, approximation error will be -25 dB. This was the assignment that was given to you in order to perform it into the laboratory, and hopefully you have done it. And I am just giving you the hint how will you make the report. Now for the hand window, the peak side lobe will be -31 dB, and 8 pi by m will be the approximate width of the main lobe, and peak approximation error will be -44 dB here. Hamming window -41, and it is the -41 dB is the peak side lobe amplitude here, and the 8 pi by m will be the main lobe width, and -53 will be the approximation error in dB. For the Blackman, -57, and it is the peak side lobe amplitude, and 12 pi by m is the approximate width of the main lobe, and peak approximate error will be -74. Now if we see this graph, this comparative graph, or the comparative properties of the different type of the windows, and again compare these properties with our example in which we are interested to design the filter, then we will see that here the minimum attenuation should be 50 dB. So if we come to this one, then we'll find that these are the two windows which can be selected for this one, that is the Hamming having the 53 dB attenuation, and Blackman 74 dB attenuation. But the Blackman window has some drawback, that it has the main lobe width is larger. See here, since the Blackman window will lead to an over-designed filter, this is due to the fact that for given window length m, the Blackman gives a wider main lobe which is not desired. Hence, in this example, we will select which one, that is the Hamming window. And we will select here the Hamming window. This is the way of the selection of the window. Now we are coming to the point, that is the selection of the M. Okay. So here approximate the window length, that is the selection of the M. We know that the cutoff frequency of any filter will be equal to the omega s plus omega p by 2, and we can find a rough estimation of the window length by equating the transition band of the filter with the main lobe width of the window here. In this example, the transition bandwidth is how much? Stop band edge frequency minus pass band edge frequency, that is the 0.6 pi minus 0.4 pi, and it will become 0.25. Since the main lobe width of the Hamming window is approximately how much? Come to the this one here, the Hamming window, it is near about the 8 pi multiplied by the m here. So it will be 8 pi m by m. It must be 8 pi by m. So we have to calculate the m, and we will get here the m approximately How much? That is the 40 here. Now this means that the design filter will be of the, what must be the length of the filter? This must be the 41. The length of the filter must be the 41. Since m is 40, so the length must be the m plus 1, that is the 41. So far we have determined the type of the window and the length of the windows. Now we have to describe the window, Wn. What is the formula for the window? That is the which window? It is the having window. Coming to the here the mathematical description of the having window. See, this is the mathematical description of the having window. That is the 0.54, 0.46 cos n pi n upon m by 2 in the finite range of the n, otherwise this will become 0 here. So according to this formula, here we will describe the Wn 0.54 minus 0.46 cos 2 pi n by m here by m. And now we will after defining this one, next is the find the appropriate ideal filter here. What will be the appropriate filter here? The cutoff frequency, as we had discussed, that it will be the omega s plus omega p divided by 2. So what will happen? In this example, we need to find the impulse response of the ideal low pass filter with omega c equal to 0.5 pi. And now in the, as per the previous example in which we have derived the SD, that is the here the desired frequency response of the filter, this will become omega c upon pi, sinc omega c upon n pi here. And we know the value of the omega c is the 0.5, so this will become here 0.5 pi, so this will become the 0.5 sinc n by 2 here. Now this is the impulse response of the filter. Now apply a time shift of the m by 2 and multiply the derived impulse response by the window here. To have a causal linear phase response, we need to apply a time shift equal to the m by 2 in the ideal impulse response and multiply the result by omega n. Therefore, we will find 0.54 minus 0.46 cos 2 pi n by m and multiplied by 0.5 sinc n minus 20 by 2, n minus m by 2. That is the n, m is 40, so by 2, n minus 20 by 2. So this is the Hn which we have derived from the previous steps. So what we have done here, that first we have selected the window, and how we have selected the window? With the a clue or that is given here, that the attenuation must be at least 50 dB in the stop band. With the help of this one, now we have the option of the two windows, and we have selected the Hamming because it is better than that of the Blackman in the case of the performance here. And after selecting the type of the window, Hamming window, now we have to select the length of the window. And for the length of the window, we have selected it with the help of the main lobe bit, that is the 8 pi by m, it must be the 40, and from this one we have derived that m must be the 40. And we have written here the here the equation of that Hamming window that was derived in the table in mathematically. After that, we have to find the appropriate ideal filter here in terms of the impulse response, and it will be that here the inverse Fourier transform, that is the omega c upon pi sinc omega c upon n pi, that is the that will be here the appropriate ideal filter, inverse Fourier transformation of the ideal filter. Now this filter will be shifted by the m by 2, that is the truncation will take place, and whatever is the result, that will be multiplied by the window here. So this is the window, and this is the shifted value of the, or the truncated value of the ideal filter multiplied by the window. So this is the windowed impulse response, or we can say the frequency response of the desired filter. Impulse, not frequency response, it is the impulse response of the desired filter. And in order to analyze the performance of this one, we have to analyze the frequency response of this derived or the designed filter. Now, in order to get the frequency response, we will apply here the Fourier transformation, and the frequency response, that is the amplitude of that Fourier transformed impulse response, will be the amplitude response, and this graph 1 represents the amplitude response. And now we will compare this response with the required response, whether we are getting the response as per our requirement or not. If it is in the permissible range, it's okay. Otherwise, there is a need of the modification of the window, or we have to select another type of the window here. Now, the simulated frequency response exhibits an attenuation of the 55 dB. And what must be the? It must be the closer to the 50 dB. And naturally, it is in the stop band, which is very close to the rejection predicted by the peak approximation error of the Hamming window. As shown in figure 1, that is the previous figure here, and figure 2, omega p and omega s pass band and stop band edge frequency are slightly different from the design specification. However, the differences are negligible. Here, after the designing, we have to mention the differences which we have derived or which we have observed in the frequency response of the design filter in comparison with the desired frequency response. As discussed in the previous articles in this series, the window method leads to the same ripples in the pass band and the stop band. However, since Fi in figure 1 uses logarithmic scale, that's why in that one, if we see in this one, then the ranges is larger, minus 55 to 60, minus 65 or near about minus 60. In comparison with this one, because in the previous case, in one case we are using the logarithmic, and logarithmic variation is larger than the normal variation here. We have to note that always there is a need of the software for the verification of the design. However, hand calculations give us a better understanding of the problem and enables us to have a rough approximation of the system. So what we have to do? We have to design the filter here, that using the rough estimation, that is by hand, and then we have to utilize the available software in order to verify our design. When we design our filter or any system by the hand calculation, then we check each and every steps which we have gone through during the time of the study of that concepts or study of the designing of that system here. And here the software just helps us, and it provides us a graphical user interface, or sometimes it provides us a dialog box so that we can enter the properties. But what are the steps? Those steps are not observable during the time of the designing. These steps are derived, calculated, and computed by the software. So in order to understand the each and every step of the designing, we should use the hand calculations for the simple examples in order to understand the each and every steps. And then naturally, for the purpose of the verification and the analysis, we should use the available software. and that software may be the .m file, that is a arrangement of the commands, or that may be a toolbox available in the form of the dialog box, or available in the form of the graphical user interface, or we can also use here the block diagram, that is the Simulink, using the .mdl file. So here it enables us to have a rough approximation of the system, and in this example, simple hand calculations enables us to roughly approximate the value of the M. There is a double M, but it is the single M here, capital M. We have approximated the value of the M. Due to the approximation, and during the time of the selection of the window, we have selected the Hamming window that have attenuation of the -53 in place of the more than 50. And we have also seen that the black man has the larger attenuation, that is more closer to our requirement, but we have not selected this one in order to design the optimal filter here. When we say optimum designing, it is nothing but this is a trade-off, this is a trick that has to be used by the design engineers. That is a trade-off between the cost and performance here. So in order to design the optimum filter, we have used the Hamming window here, and after selecting the Hamming window, we have decided the length of the window, and then we have approximated the ideal filter by taking the impulse response of the ideal filter here, and then we have truncated it, we have shifted it, we have converted it into the causal form, and then this truncated impulse response has been multiplied by the window function, selected window function, and this will be the impulse response of the desired filter. And in order to see whether the response of the filter which will be designed by this method will be approximately same as per the given requirement or not, there is a need of the observation of the frequency response of the design filter. So we have utilized here the transformation of the time domain representation into the frequency domain representation for the purpose of the frequency response analysis. And here we have utilized the magnitude response, variation of the magnitude response with respect to frequency, and we can draw this graph either in the normal graph form or in the logarithmic form. In the logarithmic form, this will become in dB, and the variation will be larger, and we can here analyze the performance more easily. That's why we use here the logarithmic representation. We have also concluded that during the time of the designing, in order to understand the each and every step, we should follow here the designing steps by hand, and after that, for the purpose of the verification, we should utilize the available software, and for this purpose we can utilize any mode of the MATLAB, or we can test it, verify our design using the .m file, .mdl file, or using the toolbox. And in the previous lecture, we have also discussed one example, and I think in that case we have also considered the same specifications. That is, the omega p was, I think it was 0.4 pi, and omega s was also 0.6 pi. But what was the difference in the previous example? In the previous lecture, that was, I think, on the Tuesday, we have used a designing method of the FIR filter, and in that case also we have utilized the value of the omega p and omega s same, that is the pass bandage frequency and the stop bandage frequency. But what was the difference? What is the difference between these two types of the designing, which we have covered on Tuesday and which we are just discussing here today? Yeah, response please. What was the difference?
Sir, Caser window was used
Yeah,
yesterday.
yeah, very right. Which window was used?
Caser,
Teaser window.
Caser window, sorry.
Yeah, who is responding?
Anshika.
Anshika. Very good. Good. So only the difference is in the window. And see, here we have not to select the window randomly, but we have to select the window according to our need and requirement. Why we have selected here this window, having window? Because we have a restriction that passband attenuation must be greater than 50 dB, and we have considered here only the sinusoidal windows. And what is the specialty with the Kager window? That provides a trade-off, that is the optimal solution between the main lobe width and the side lobe attenuation. And in this one we have selected the Hamming window here. So during the time of the selection, we have to see each and every requirement or the specification whatever is given. Then according to those requirements or the specification or both, we have to select the type of the window. Then in the next step, what will be the next step? We have to select the length of the window. After selecting the type and length of the window, we have to calculate or compute the appropriate ideal impulse response of desired filter. Then that desired filter's impulse response will be truncated by applying the shifting concept, shifting by m by 2. And since we have already derived the value of the m, so we can shift it or we can truncate it in order to convert it into the Fourier form, and windowed impulse response will be achieved when this truncated impulse response will be multiplied by the selected window, not by any random window, by that selected window which we have decided in the first and second step. Then we will get here the impulse response. Now whatever is the impulse response, it is nothing but this is the coefficient related to the filter for which we are interested, or we can say these are the coefficients of the filter which we have designed. Now we are interested in order to see the performance, means how the amplitude and phase are changing with respect to frequency for this particular design filter. And for that purpose we have to select the frequency response. That is, now we will apply here the Fourier transformation, and after applying the Fourier transformation, naturally this will become here the complex function. And since it is a complex function, that will have the terms like e to power j omega. Now it has the two sections, one is the amplitude and the second one is the phase. Now we will analyze the variation of the amplitude with respect to frequency. What is the amplitude response? That is the analysis of the amplitude response. And at the same time we will also analyze the phase response, means how the phase are changing with respect to frequency. Then after observations we have to conclude, we have to make a comment whether the responses are within the permissible range what was expected during the time of the requirement or not. If these responses are in the permissible range, within the permissible range, it's okay. Otherwise there is a need of the modification. And how the modification will take place? First we will try to change the value of the m. In order to enhance the performance of the filter, we have to increase the value of the m. And if we are not getting the range or the required limit of the permissible range by enhancing the value of the m, naturally we have to select the another type of the window. Again we will go to the requirement, and according to the requirement we will select the window here. So these are the steps. And again after selecting the window, length of the window, then HN, then shifting, then multiplying shifted Hn by the Wn. Again, we have to analyze the performance here, that is the amplitude variation and the phase variation with respect to frequency. Then finally, we will conclude that it is in the permissible range, what was expected. So this is the design filter. This is the concept of the designing. And as we have discussed in the very beginning, that we have to utilize one trick. And what is that trick? That technology, that is a trade-off between the cost and performance of the system which has to be designed. So this is the concept, or this is the method which we have discussed in order to design the FIR filter using the window method. And we have considered the two examples. In the first example, we have used the Kaiser window, and in the second example, we have used the here the Hamming window here, as per the need and as per the requirement. So accordingly, we can select the another type of the windows here. And if you people have any query, any doubt, then please ask it.
Why do we need to decrease the main lobe width of a filter?
Yeah, good. Very good question. Now we are just coming to this one, that is, see here. This is the approximate value. Okay. I think it is visible. No visible. No? Not visible. Presentation. It is visible. No. Again presenting. One very good question has been raised by, I think, C. Jansiga. Again, am I right? Yeah. Is it visible?
Yes, sir.
Yes, sir.
Okay. Thank you. Now see, this is the approximation which we have derived from where? From the requirement. See, this is the first step, the requirement, and this is the specification. If you recall about the first lecture in which we have started our journey from the very first level, and what was the first level? That was the requirement. And at that time, we discussed that requirements are always ideal. For example, if we are in a class and we appear in the examination, then what is our requirement? 100% mark. But there are some practical limitations. That's why there is a need of the modification. Approximation has to be used here. And by the approximation, we are getting this one by the blue in color. Blue in color solid line having larger width. And dotted black line, it shows the ideal response of the low pass filter. Is it okay? Now come to this point that during the time of the designing, what must be the first step? We should avoid this one. Which one? The negative portion, because it is anti-causal, physically not realizable. It is totally hypothetical, right? So we have to consider which one? This one, from 0 towards this side. Okay. Now, what is our approach? We are trying to minimize the ripples in the pass band, so that we can get nearer to the ideal filter. Is it okay?
Yes, sir.
Yes or no?
Yes, sir.
Yes. And the second requirement, similarly, we will also try to minimize the ripples in the stop band, so that we are approaching towards the true value or the ideal one. And what is the transition bandwidth? It must be the 0, but 0 is not possible. So we will try to minimize this transition bandwidth. And how is it possible? By selecting the lower main lobe, because this is the main lobe. This describes the main lobe here. Come to the windows here. This is the main lobe, starting from 0 to this side, As main lobe is lower, then what will happen? Transition bandwidth will be smaller. Is that clear?
Yes, sir.
Is that clear?
Yes, sir.
Yeah, good. It was very good question. Okay, thank you. और कोई भी प्रॉब्लम हो हमेशा क्लास में पूछें, ये नहीं कि हम अलग से पूछ लेंगे, किसी दिन मेल कर देंगे, किसी दिन व्हाट्सएप कर देंगे, उससे कुछ नहीं फायदा होता है। तो जब क्लास में पूछते हैं हर एक स्टूडेंट्स उसको समझते हैं और क्लास में अच्छे से एक्सप्लेन भी किया जा सकता है, ठीक ना। तो आप जो भी डाउट हो हमेशा हर एक स्टूडेंट्स को प्लीज, आप लोग बार बार एडवाइस कर रहे हैं, रिक्वेस्ट भी करते हैं, आप क्लास में जरूर पूछें, ठीक है।
Yes, sir.
अच्छा, कुछ लोगों का सेमिनार है, तो सेमिनार का प्रेजेंटेशन आप लोग जानते होंगे, शायद कुछ बच्चे हैं जो कल हमारे साथ भी होंगे। सेमिनार में आप जब प्रेजेंट करने जाएंगे तो पीपीटी ऐसे बनाइए बेटा जैसे हम लोग बनाते हैं, ऐसा नहीं कि कैसे कॉपी कर लें। आप मेन पॉइंट्स आप रखिए, जो पॉइंट्स बोलने जा रहे हैं। टाइटल होना चाहिए, टाइटल के बाद आप उसके विषय में आप ब्रीफली डिस्क्राइब करिए, व्हाट इज द टॉपिक, इंट्रोडक्शन, देन हिस्टोरिकल बैकग्राउंड, and after historical background what is the main work related to that topic, उसको describe करिए। what are the works which has been done in that field, means what is the status, जो भी आपके पास पॉसिबल हो नेशनल लेवल पे, इंटरनेशनल लेवल पे, उसको आप प्रेजेंट करें, फिर लास्ट में कंक्लूड करें, एंड फाइनली यू हैव टू मेंशन द रेफरेंसेस कि कहां से आपने ये पॉइंट्स लिए हैं, उनको भी मेंशन करें। और फर्स्ट पीपीटी में आप जानते ही हैं कि आपको टाइटल देना पड़ेगा, व्हाट इज द टाइटल, आपका डिटेल्स, कौन कौन लोग प्रेजेंट कर रहे हैं, इन द सुपरविजन आर गाइडेड बाय, उनका नाम लिखेंगे, ये आप डिपार्टमेंट ऑफ इलेक्ट्रॉनिक्स एंड इंजीनियरिंग डिपार्टमेंट नीचे लिखेंगे, ये करके आप प्रेजेंट करेंगे। बाकी सर लोग आपको बताएंगे ही, ये आपको हमने ऐसे चलते चलते बताया कि कल से शायद हम लोगों का सेमिनार शुरू हो रहा है ना अपने लोगों का, यस सर नो, कल सेमिनार है ना, बोले रहे बच्चे, क्यों देवचंद जी? हेलो, चलिए कोई नहीं, ठीक है। चाहे आप सेमिनार में हो, चाहे प्रोजेक्ट में हो, चाहे डिसर्टेशन में हो, या कोई भी वर्क आप प्रेजेंट कर रहे हो, तो जब भी आप प्रेजेंट करें तो आपको यही स्टेप्स फॉलो करना है कि पहले हम क्या कवर करेंगे, टाइटल, आफ्टर दैट वी हैव टू डिस्क्राइब द इंट्रोडक्शन रिलेटेड टू दैट टॉपिक, फिर हम हिस्ट्री भी उसकी डिस्क्राइब करेंगे इसी में, फिर ये डिस्क्राइब करेंगे व्हाट इज द स्टेटस ऑफ दैट वर्क एट द नेशनल लेवल, इंटरनेशनल लेवल की जो कुछ भी हमारे पास जानकारी होगी हम ऐसा प्रेजेंट करें कि कोई जो सुनने आए तो उससे रिलेटेड वो अपडेट हो जाए। फिर और ये हर एक के लिए बड़ा फायदेमंद होगा, जैसे आप प्रेजेंट करेंगे दूसरे का फायदा होगा, दूसरा प्रेजेंट करेगा तो आपका फायदा होगा, सब ये सुनेंगे भी और अच्छा भी लगेगा और हमारे टाइम का पूरा उपयोग भी होगा, नॉलेज भी बढ़ेगा अपना, ठीक ना। फिर उसके बाद स्टेटस डिस्क्राइब करने के बाद मेन वर्क क्या क्या है उसमें से रिलेटेड उसको डिस्क्राइब करें, फिर लास्ट में कंक्लूजन जरूर बताएं कि इसमें क्या क्या आपने डिस्क्राइब किया, क्या फ्यूचर में और काम होने वाला है, वो सब कंक्लूजन में आना चाहिए। फिर सब कंक्लूजन के बाद आप डिस्क्राइब करें व्हाट आर द रेफरेंसेस, ठीक है। एनी मोर क्वेश्चन, और कोई क्वेश्चन? ठीक है, थैंक यू।
हेलो, हाँ स्टूडेंट्स, एक बार आप अटेंडेंस आप आज की देख लीजिए अपनी, ठीक है, मैं बोल देता हूँ।
थैंक यू एवरीबॉडी।
अटेंडेंस छुट्टी हो तो बता दीजिएगा आपको। ठीक है, तो मैं अटेंडेंस बोल दे रहा हूँ। अभिषेक मिश्रा, अभिषेक वर्मा, आदित्य पांडे, ऐश्वर्या द्विवेदी, देन आकाश सिंह, के बाद अमन कुमार, अमित गुप्ता, अनीश कुमार, अंशिका पाठक, अंशुल प्रजापति, अनुज कुमार, अपर्णा, सॉरी अनुज कुमार, देन आर्य कार्तिकेय,
थैंक यू।
चंदन मौर्य, हर्ष सराफ, हर्षित दुबे, Then
Thank you, everybody.
Manish Kumar, Manvendra Pratap, Nancy, Nabya, Parikshit, Pranjal Gupta, Prapti Singh, then Salim Khan. After that, the Satyarth Katiyar, Soumya Sharma. After that, Tarun Tiwari, Utkarsh Sharma, Utkarsh Srivastav.
Thank you.
Then Basu Agrawal and Yogeshwar Rai, last student. ठीक है, इसमें किसी की अटेंडेंस छुट्टी हो तो बता सकते हैं आप लोग.
Thank you.
सर प्रतीक गुप्ता.
Thank you.
क्या नाम? प्रतीक.
सर प्रतीक.
एक मिनट.
सर उमेश कुमार.
चेक कर लेता हूँ आपको. बने रहिएगा आप. अभी मैं अटेंडेंस आपका ले ले रहा हूँ.
सर उमेश कुमार.
उमेश कुमार. ठीक है, प्रतीक और उमेश दोनों लोग बने रहिए.
क्या कुछ अभी रोक रहे हैं क्या सर?
नहीं सर, बस केवल अटेंडेंस हमने कहा एक बार चेक कर लेते हैं जिनकी छुट्टी हो.
अच्छा.
यस सर, बस चेक कर लिया, लगा दिया हो इनको. दे कैन लीव सर.
हम क्या क्लास छोड़ सकते हैं क्या? कोई वेट?
यस सर.
Thank you.
You can leave and students also can leave.
Thank you everybody. So now I am leaving. Thank you once again.